Thank you. Yeah, hi, good afternoon, and thank you all for being here. I'm going to be sharing some results from my this very simple comparison study that I'm doing as part of my PhD research, where I'm looking at the ice edge in different analysis and observational data sets and trying to compare them against each other. But before going to the topic, let me start with a little motivation. Somebody recently said that we stand on the shoulder of giants, and I definitely stand on the shoulder of Lorenzo. So the story began when he looked at the ice edge in different models from the subseasonal to seasonal database, and he found that among all the models in this database, ECMWF was performing very well, except it started with, is there a pointer? It's okay. He found that it's starting with a substantial error right on day one. We found a similar result in another study as well, so we said, okay, what's going on? Let's look further into this. So we started, this is supposed to be a PowerPoint with multiple things popping up and out, but it didn't work. We started by saying, okay, let's look at the ECMWF initial day error, but then we said, okay, the ECMWF forecasts are initialized from the ORAS-5 reanalysis. Let's look at those. And then we started looking at other observations against this, and then it became a jumble, and now we're looking at various models against each other, including the IMS ice presence from the US National Ice Center, the climate data record ice concentration from NSIDC, and ice concentration from University of Bremen, AMSR E and 2. So everything has been, just for a little methodology, everything has been mapped to a common grid, and we're using 15% ice concentration to determine ice presence, and using integrated ice edge error as our verification metrics. Integrated ice edge error, as many people already know, is the sum of area of mismatch. So you look at from the perspective of one data set to another, you look at how much you're overestimating and how much you're underestimating. So you can also look at those two components separately. So to start with, let's look at the integrated ice edge error of ORAS-5 against OCSAF. And here I'm just showing the control run, but it's similar across the ensemble. Measuring the error against OCSAF on each day, and we also looked at climatological error based on the previous 10 years. We see that the analysis errors are quite high and almost equal to climatological error at some points, especially in the northern hemisphere. So let's kick out the climatology for now and bring in other observations. We see that, okay, this is true when compared against other observational data sets as well, that the errors are substantial and there's a very clear seasonal pattern to it. So if we just look at the mean seasonality, we see that the ORAS-5 ice edge has an integrated ice edge error of around 500,000 square kilometers in the winter. It goes up quite substantially in the summer, then decreases downwards towards October in the northern hemisphere, and then kind of goes back up again in the winter. Similar behavior in the southern hemisphere, except there is a winter peak as well. And another interesting thing was that when we look at the different observational data, we see that the error is not the same. There's a little bit of difference between them. We can also look at how much of the error is due to overestimation by the analysis. Here we see that in the summer, the error is led mostly by underestimation. So yeah, it's on the lower side of the overestimation chart, but in the winter, it's led more by overestimation. Also true in the southern hemisphere. So in short, the analysis has too much ice in the winter and too little ice in the summer. But if you compare between the different observations, you see that there's a difference in the behavior. If we look at the ice presence bias, here we're looking at the mean for July. We're just comparing July because it's the month with the highest mismatch. we see that, okay, ORS5 minus OCSAF and minus NSIDC, we see this very strong negative bias, especially around the coastal regions. When we compare against AMSR, we don't see the same strength in the bias. So this is a little interesting. And also, when you look at OCSAF, for example, there's this very strong bias in the Gulf of Finland, for example. So I'll come back to that point in a little bit. But overall, we see that there is more of a negative bias. So there is an underestimation of ice. Similarly, in the southern hemisphere, again, the highest error was during December, so we're looking at December. We see a very strong negative bias against OCSAF, almost as strong against NSIDC. And then when you come to AMSR, now we see more of a slight positive bias. So this is a little confusing. But in some regions, for example, in the Ross and the Weddell Sea, we see this very distinct and clear pattern of negative bias. So this we can be sure, okay, this is something wrong there. Little halfway summary. So we see considerable error from the daily analysis from ORS5, and the mismatch is highest in the summer, led by underestimation. But some observations show more error than others. So do the observations themselves agree? Let's find out. So now we're comparing the observations against each other. So this figure shows the integrated ICES error of OCSAF compared against the other observational data sets that we're using. So first of all, we already see that the OCSAF data itself has a lot of mismatch against the other observations. So we're looking at observations on the same day. You would expect that errors would be quite low, but it's actually substantial. Depending on the different data set, the error is different, and there's a very clear seasonal pattern to it as well. So we can look at the seasonality, but here I'm showing you all the pairs at once, just to give you an idea that, okay, there is mismatch in all the pairs. In every pair, you see that the summer around July is peaking, July in the northern hemisphere, December in the southern hemisphere, it's peaking, and the errors are quite large. Just for the case of OCSAF, we looked at it, and the errors are always led by an overestimation by OCSAF. So OCSAF ice extent is generally always higher compared to the other data sets. And the overestimation is highest during the summer, but there's also a slight peak in the October and the freezing season, and also true for the summer peak in the southern hemisphere. So we decided, okay, let's look at the ice presence bias, and here we're looking at the mean bias for July in the northern hemisphere. And we see that, okay, compared against NSIDC and AMSR and IMS, we see that OCSAF has a positive bias throughout. And remember how I pointed out the Gulf of Finland earlier? You see that compared to all the observational data set, there is a very strong positive bias. So if you just look at one of these figures, you say, okay, in this case, there's a positive bias, but is that because OCSAF has too much ice or NSIDC has too little ice? It's hard to say, right? But when it has this bias across the board, then you can kind of estimate, okay, there is something seems to be wrong over there. Similarly, in the southern hemisphere, we see that OCSAF has a slight positive bias against NSIDC, a very strong bias against AMSR. Now the third figure is NSIDC minus AMSR, and we see that some of the positive bias patterns that we saw with OCSAF are also repeated by NSIDC. So again, with triangulation, we can say like, okay, in this case, we can estimate that AMSR is underestimating ice. I don't have the figure for this, but we did a similar comparison in the northern hemisphere, and we also think that AMSR ice estimates are lower than they should be. So just to summarize, there are considerable differences in ice presence between the different observational data sets, and comparing the mean bias maps can give an idea of where certain data sets have issues. For example, the Gulf of Finland for OCSAF or West Antarctica for AMSR. And it is likely that these disagreements or errors in the observations themselves kind of get carried forward into analysis and into forecast. So looking back to the first figures we saw, it could be that some of the error we measured for ECMWF is not actually that high. So the forecast performance is possibly better than what we saw. And thank you.
Your figure suggests that you were looking at the sea ice concentration, but then you also said sea ice extent. So which one of the two did you look at?
Sorry, I think I didn't make that clear. I'm only looking at sea ice extent and presence. So using concentration just to derive the presence.
Oh, so and there's big bias even in the extent.
Yeah.
Okay.
So I looked at the differences between OCSAF and IMS as well, and I did see that one you saw a underestimate of ice, and I saw that too, and that was, but what I noticed about that one was it was extremely threshold dependent. If you up the threshold a little bit, it went completely wild. It was a very big bias, and so I interpreted that a lot of that to do with no melt pond problems in OCSAF. So I don't know. I'm a little bit confused about how you get to the negative bias with these other products, unless they even have a worse melt pond bias. But I don't know.
Yeah, I'm not sure. I have to think about this a little bit more. But I did look at using different thresholds. The problem is with IMS, it's already fixed, right? So you're only changing the threshold on one side. So, which is a good strategy probably.
But they're kind of advertised. Alain tells me that that's true. Their advertised threshold is actually 0.4. So.
Okay. Yeah. So maybe it would be a better comparison at 40% rather than.
This actually will turn out to be a worse comparison than 40%.
Okay. I have done that, but I haven't actually looked at the figures enough to say it off the top of my head how it is.
Yes, that's maybe more comment. So your different concentrations are based on different retrieval algorithms, and that's probably where your differences are in the passive microwave. And the OCSAF and the Bremen differences in the way you have a mixture of frequencies in the OCSAF, but the Bremen is the high frequency, so you get concentrations close to coasts, but they're more noisy.
Yeah.
That's a general sort of.
And also the Bremen people, they're aware that their estimates are lower actually. They have written that down somewhere.
Sorry, which version of OCSAF did you use, by the way?
This is the CDR, so 450 and 4.
That's the reanalysis, right? So that's the one that's kind of gone back.
Yeah, it's valid, like, it's validated, revalidated somehow.
Yes, so do you think there is some possibility of creating a probabilistic observation? Is it an option, and is it possible to do with just 3 products?
That's something I thought about, and but it is easy to do that with just ice presence, right? You just take the ice presence with 3, then you only have 3 steps. That's maybe not so good, but then it's like, how do you determine the ice presence threshold that you want to use? That's a tricky question, and maybe if I get a postdoc, I would follow through with that.